Okay, Biology of Fishes, the 27th of September, 2012. We've got sort of a thin house this morning. Maybe we'll be joined by some more folks before we're done. I'm opening up a different page than I usually show. That's the home page for the course. And the reason I open it is that it includes the syllabus, prospectus, and schedule. And I wanted to have a look at that schedule with you. And I wanted to note that, today is the 27th of September, and in a couple of weeks now, on the 11th of October, we're going to have an exam that will cover the material that we get to probably the day before we have the exam. So there are two messages there. One is for everyone. You need to start thinking about reviewing and checking on things that you may have missed if you were absent for a session, or if you're behind on playbacks, then you want to do that and keep up. The other thing I need to say, and the reason I'm bringing this up particularly today, is that I got to remind the distant folks who will not be taking the exam here in the room with me and with Donovan probably, that you're going to need to arrange for a proctor. Not necessarily someone that's going to look over your shoulder and monitor everything you do, but somebody who's going to be generally responsible for you, for getting the exam from me, for administering it to you, and then picking it back up and emailing or faxing it back to me. That way we'll reinforce a sense of security. I don't know that we need to do that with adults, but I feel an obligation to do it. So that's the two things I wanted to say about the exam. Get ready for it. Have a look at. Now we'll go back to the archive page and remind you that there is a sample exam posted for you to look at, so that you can make sure that you understand how everything's going to work when the time comes. And not only that, but if you look on down on the 2011 material, you'll see that there is something called regarding the exam. And it was a file that I recorded, a piece of a presentation I gave the last time I taught the course, when I talked about the exam. And there might be some things in that worth your hearing. It's not very long, as I recall. The other good news I've got to share with you today is that this stuff up here about AVI files and, nothing else, that's all changing, thank goodness. And it was driven by the need to work with Windows 7, which is what most of the students here in the course now are using. And the fact that Windows 7 balks when you ask it to play back AVI files with OpenView at faster than normal speed. And I hope you noticed the email that I spent quite a bit of time putting together, sending out, basically saying that I think we've beaten that problem. Thanks to Ray Camps, who isn't with us this morning, but I have a debt, not a department to Ray. I used the wrong word in my email. I meant DEBT instead of DEPT when I said a debt of gratitude for coming up with this. So basically what he discovered is that if you convert, or if I convert, which is what I've done, or starting to do, the AVI files that are produced here into Apple MOV files, then those MOV files can be played back with Windows 7 or Windows XP, or now I find even with Macs. And you'd expect that, because after all, the QuickTime is made by Apple. And so what you need to do, if you want to play back these files on your Windows 7 machine at faster than normal speed, is instead of downloading the AVI, which is what this link will give you, slip over there and click on the MOV link. It's a bigger file. That's the only real downside. About 2 or 3 times bigger typically. Takes longer to download. It'll take more file space to store for you, but it'll be well worth it, especially if you're running Windows 7. And especially if you're trying to use a Mac. Even if you're using XP, it's still a good deal despite the bigger file size, because one of the real advantages that Ray discovered with these MOV files and QuickTime is that there's an automatic compensation for the speed up that adjusts the frequency so that you don't get the Donald Duck voice quality. It'll be more like a normal voice except talking faster. So I think you're really going to like that. And I'm starting the process of going back and producing these things. It takes some time to do it. So I'm starting now and moving back. You'll see there that I've got the September 25th and the September 20th presentations, which won't be of any interest to most of you in the room, or all of you, I think, because I think you were all here. But down here on the lab is where it'll really be handy. I've gone back and I've converted to MOV all of the help files from Lab 1, as well as the ground truth file. And then in Lab 2, I've even done the proceedings, because some people still have not done or haven't gotten to that point in Lab 2, I'm sure. I got at least one person who's still working on Lab 1, so that was the reason I went back and did that one. But almost everybody that hasn't already finished Lab 2 completely is going to be glad to use the MOV versions of the help. I only did that for the 2010 Excel help. I didn't go back and do it for the 2003, because I figure anybody that's running 2003 help's probably running Windows XP. So any questions among my local folks that will be ones that anticipate questions from distant students, I'm sure, about any of this. I'm really excited about this advancement, about this big move forward. And Julie Butler, by the way, who isn't here, I give her the credit for testing this with Apple, with Mac, to see that it'll work there too. And she says, yes, it will. Although, she said the speed up on the Mac version of QuickTime is a little different from the way I explained it for Windows. And so if you want to use Mac, and I don't think anybody in the room here is probably using Mac, but anybody at a distance who's using Mac needs some help on getting it to work and playing QuickTime, playing these MOV files in QuickTime at speeded up rates, contact me and I'll put you in touch with Julie. She's our expert on that now. Okay. Enough about that. Let me take you back to the respiration session and just emphasize a few things and correct a couple of other things. Maybe not so much correction as just emphasis. I'm going to go to presentation here and do it that way. Let's see, where did I want to... I think what I wanted to do is get to... Everything was cool about this. I mean, I didn't see any big mistakes in what I was saying here. I explained to you the importance of a bore shift in terms of maximizing the amount of oxygen that can be transported per unit blood per unit time. And it's got to do with the fact that the bore shift allows the fish to load its hemoglobin close to completely in the gill, and then to unload the hemoglobin almost completely in the tissue, which maximizes the amount that can be transferred. And I can almost promise you there's going to be one of my 5 discussion questions that are going to ask you to give an example, kind of show me that you understand this transport business, why the bore advantage works, or what's the advantage of having a bore shift. The one thing I wanted to go on and say it better than I said it the other day, especially for my back row back here who all have an interest in aquaculture, is I was talking about, before you may remember me talking about a really high intensity fish production system down on the coast that at the time was managed by one of my former students, John Turner. And another former student was there as an intern at the time, Mike Swartz, now Dr. Mike Swartz, and Mike has has moved up to the big time. I think he's actually president of the U.S. chapter of World Aquaculture Society now. Anyhow, I think I already mentioned that these fish were so densely packed into these raceways, and they were producing so much CO2 that you measured CO2, free CO2, and it would be in the tens of parts per million. I mean, 20 or 30 or 40 parts per million. And that was causing the pH of the water to drop so much that John was having to really put a lot of buffering into that water in the form of sodium bicarbonate to keep the pH even bearable. And he was using liquid oxygen to oxygenate the water. And he was running those tanks at like 20 parts per million DO. And he had to do that to get maximum growth rate. So here's a really extreme case, right? And aquaculture often is really useful in helping understand biology because it forces you to look at the extremes. And in this case, what we had was a biomass of fish that approached 10% by volume of the water in the tank. I mean, we're talking about, a gallon of fish per 10 gallons of water, nearly. I mean, I saw one of those tanks drained for harvest. The tank was about 5 feet deep, and there was a layer of fish in the bottom that was about 2 feet, it seemed like, when the tank was drained. So, I mean, we're talking high biomass, and we're talking about a lot of buffering to maintain pH at bearable values, and CO2 partial pressures in the 20s, 30s, 40s, all measured, by the way. And DO at 20 parts per million. So I asked in kind of a careless way, or a casual way, I guess careless too, I said, why in the world would these fish be benefiting from a DO as high as 20, when in fact you'd think that their hemoglobin would be saturated at lower values of DO, and there wouldn't be any gain, really, in adding O2 in solution to the plasma. Because the plasma carries so little, even if it's 20 or 30 parts per million DO. And Mike Swartz said, well, Dr. Neal, you gave us the answer to that when I took biology of fishes. He says, it's the Bohr effect. And I said, Mike, you're right, I think. Because when you look at this graph, and you think about PO2s in the gills being air saturation, normal values, we're looking at a shift to there. But imagine that the PO2 is way over here off my graph on the right. There's a Bohr shift that's way over here. If you kept the DO, in other words, if you take that red curve and move it to the right, so that over here at this high DO or at air saturation, we're way down here on the curve, then what would happen? Well, fish would be limited by low DO. They wouldn't be saturating their hemoglobin if you maintained only air saturation DOs. But because they were maintaining 2 and 3 times air saturation, the fish were still getting hemoglobin loaded, and therefore they were still able to grow. And I'm almost thinking, that the real negative effect of high CO2, free CO2 in the water, the high partial pressure free CO2, it's not really, I don't think, a toxic effect per se. It's the fact that if CO2 is high in the water, the fish can't excrete the CO2 they're producing very well against that gradient. Plus, they're subject to a severe Bohr effect. I think they're suffocating basically because of high CO2 as much as anything else. So those are just thoughts for you, especially you aquaculture guys. You have to see the extreme in order to really appreciate the kinds of things that can go on, You'd never want... fish in nature would probably not benefit from 20 parts per million DO because it's already loaded its hemoglobin at 8, and everything above that is just waste. You're just bubbling it off. By the way, you might ask yourself, what's the maximum amount of DO you can have in the water under any kind of normal conditions? Let's say you're using liquid nitrogen or liquid oxygen. And the answer should come back, well, At 1 atmosphere of pressure, if all of the gas that's in solution in the water were replaced with oxygen, you'd be from 0.21 to 1.0. In other words, the best you could do would be have a 1.0 atmospheres of oxygen in the water. And if you were creating 100% oxygen atmosphere above that water artificially and not adding any pressure. Now, if you pressurized it, you could go higher. But if you didn't pressurize it, I think all you'd ever expect would be 4 times, or I guess 5 times, air saturation. So if air saturation is 8 parts per million, then maybe you could achieve 5/8 is, what would that be? Somebody help me here. Somebody do the math here. Just checking to see if you're keeping up with me here. Are we talking about 40? 5 times 8, 40 parts per million DO, in theory, would be possible if you were using liquid oxygen and sealing the atmosphere above the tank, above the water, so that the exchange was between 100% oxygen atmosphere and the water at equilibrium without increasing the pressure. So 1 atmosphere of pressure, 100% oxygen atmosphere, at steady state, you ought to have 40 parts per million DO if you got 8 parts at normal. All right, so that was one thing I wanted to say. And maybe that's really the only thing I wanted to say. First, I made a mistake when I said, hey, the root effect may be involved here. I don't think it is, because by definition, the root effect says that no matter how much PO2 you got, I mean 40 parts per million, you're still only going to get a load to that level. So having 40 parts per million wouldn't help you if there was a big root effect going on, because you just wouldn't be able to load your hemoglobin past that point. So I guess the Bohr effect, I think Mike Schwartz was right. I don't think there was anything else here that in this first part that I wanted to say again. I wanted to follow up on the gas bowl disease, and particularly where I was stumbling here toward the end of the session because I hadn't had a chance to review this lately. I'm getting old and forgetful. And I think I was right on everything. Well, I didn't say anything really wrong, but I didn't really say it that right either. Henry's law says that concentration of a gas in solution is proportional to the pressure of that gas in the atmosphere with which that solution is in exchange, and that's the best way to say it, rather than in equilibrium. The proportionality constant is alpha, and we call that Bunsen solubility coefficient. And I made the point that it's not linearly related to temperature, but I didn't emphasize what I meant by that. And the best way, I looked back at my notes and I found out that, let's say you take water at 2 different temperatures. And I think the temperatures I used were 10 and 30. You mix that water together, and by the way, you got air-saturated water at 10 and air-saturated water at 30. And you mix together equal amounts of the 2 water masses. Well, logic should tell you the temperature that ought to result is midway in between, right? 20 degrees. But the nonlinear relationship between alpha and temperature means that that water will be like 105 or 106 or 7% saturated with air. In other words, you take 100% air-saturated water at 10, mix it with 100% saturated water at 30, you get 20-degree water, but it's 105 or 6% saturated. Somewhere above 100 at least. If it were linear, it'd be 100% still, right? Logic says. Relative saturation, remember that's the one that's, if nothing changes, if it's the same atmosphere that you're exchanging with and the same partial pressure of gas in solution, then that's the one that's going to be the same from top to bottom. If it's 100% at the surface, it's going to be 100% at the bottom. Absolute saturation, though, depends not just on the pressure of the gas in solution, the pressure in the gas in the atmosphere with which that solution is in exchange, but also the pressure exerted by the hydrostatic force of the water, the weight of the water pressing down. And the weight of the water pressing down amounts to 1/10 of an atmosphere per meter, approximately. 1 atmosphere per 10 meters. So you calculate the absolute saturation by taking the partial pressure of the gas in solution, say 0.21 atmospheres in the case of oxygen, and then dividing that by the sum of the partial pressure of that gas in the atmosphere with which that solution is exchanging, which would still be 0.21, and then adding the pressure of water, which would be 1/10 of an atmosphere for every meter you're going down. So, at the surface, you'd have an absolute saturation of 100%, but as soon as you go down a meter, that's going to drop because you're going to be dividing by 0.1 plus 0.21. Go down another meter, it's going to be dropping even further. It's going to be almost a half of 50% because there you're going to be at 0.21 plus 0.2. So that'd be 0.41 divided into 0.21, right? So that's about 0.5 multiplied by 100 is 50%. I said it's nonlinear because if you go down to let's say you go a full 10 meters down, okay, now you're at 1 atmosphere due to water, still at 0.21, so 1.21 divided into 0.21 times 100% is like what? Somebody do the math in their head for me. 0.21 divided by 1.21. Trying to think here with you. I can get my calculator out. We could waste a lot of time. I was hoping somebody would have better math sense in their head than I do. Okay, let's see. 0.21 divided by 1.21. That's almost 6 to 1. And so that's about 0.18. So about 18% saturation, I think, at 10 meters. Absolute. Now remember, it was 50% at 2 meters. So obviously it can't be, if it was 50%, it had to be 50% at a deeper depth in order for that to be linear. I challenged you to work out the curve, but probably you didn't do that, Chet. I didn't either. But if it's 100% at the surface and it's 0.5 at 2 meters, then I would expect it to be 0 at 4 meters. But it's not even 0 at 10 meters. It's still about 1/6 or about 18%. So obviously it doesn't work quite like the rule says, which is 1/10 of an atmosphere per meter, or 10% change in the relative or absolute saturation per meter. That's not quite true, obviously. It's only true right at the surface. Okay, now we finally got down to gas bubble development, or gas bubble disease is what GBD stands for. It's the absolute and not the relative saturation that is important, because the likelihood or the tendency of a bubble to form, the propensity for bubble formation, is defined as the difference between the pressure of the gas in solution less the pressure of that gas in the atmosphere with which that solution is in exchange, less the hydrostatic pressure of the water, that 1/10 of an atmosphere per meter. And the rule is BP below 0 means there's no propensity for bubble formation. The BP above 0 means there is. But the thing I didn't get to or didn't say strongly enough is that just because there is a positive value for BP doesn't mean you're going to get a bubble. Actually, that's the value that is proportionate to the growth of a bubble that already exists. In other words, if you've got a seed bubble sitting there, then if BP is greater than 0, that bubble is going to get larger. But if you've got no bubble at all, no seed bubble to start with, then it may take a much greater value of BP than 0 in order to start a bubble from scratch. A de novo formation of a bubble, as it's called. In fact, somebody calculated that you got to have 100 atmospheres of BP in order to get a bubble to start from nothing. So why do you ever get bubbles? Because Well, because there's always little micro bubbles there, apparently. And somebody else has done the particle physics of what happens in solutions when they make sharp turns like they do at the junctions between the blood vessels. You get a little vortex, and on a molecular level almost, micro level, there could be a big negative pressure that would take a bubble and cause a bubble to form. In other words, the pressure is so low that gases come out of solution, forming a little seed bubble. And then once that seed bubble's there, then BP greater than 0 in general could give you the growth of that bubble, and you end up with bubbles lodged in the capillaries of the brain, or bubbles lodged in the capillaries of the kidney, or in the gill filaments, and that causes gas bubble disease. So it's not good to have a BP greater than 0 if you can avoid it, or avoid situations. And I'll end up, I hope today, talking about one situation where it turns out that there's a mechanism for avoiding gas bubble disease in phycoclists, but not in physostomes. Phycoclists are fish that have swim bladders with no connection between the swim bladder and the gut, no tube, no pneumatic duct. Physostomes are fish like salmon and catfish that do have a tubular connection. So let me give you an example of what happens with depth and gas bubble disease. This fellow named Ebel back in 71 published a paper in the gray literature, this NOAA technical report. And what he talked about was a controlled experiment with Chinook salmon in cages in gas supersaturated water. So he had these Chinook salmons that were in water that had a relative saturation of 130% expressed as air total partial pressure. So that keeps the calculations easy, right? Because there's 1 atmosphere of air at 100%. Well, this is 130%. So 30% supersaturation of air in the water, relative saturation. He put these fish in cages of 2 types. In one cage, the cage went all the way from the surface down to a depth of 4.5 meters. And he left them there 7 days. In the other cage, it was the same kind of cage, but he had an artificial ceiling in it, a piece of netting across it, so the fish could not get higher in the cage than 3 meters. In other words, they were restricted to the bottom of the cage, between 3 meters and 4.5. And the results were that 68% of the ones in the deep cage, the ones that were able to swim all the way up to the surface if they wanted to, died, or I guess they died of gas bubble disease in 7 days. Whereas in the cage where they were confined to the bottom, only 2% did. So, what's going on there? Well, this I think is the kind of thing that is convincing, if not proof, that hydrostatic compensation helps keep gases in solution. And so, therefore, it's the absolute percent saturation that matters and not the relative saturation. Because if you calculate the absolute saturation at 3 meters, and you do this just with the total pressures of all gases, so you're talking air instead of oxygen or nitrogen, you get 1.3 as the partial pressure, 1.3 atmospheres is the partial pressure of total gas, relative to 1 in the atmosphere with which that water is in exchange, plus 0.3. 0.3 meters, 0.3 atmospheres, because at 3 meters deep there's 0.1 times 3 hydrostatic pressure. And so you can see that the result is that gives you 100%. And so therefore BP, the propensity for bubble formation, would be 0. Bubble formation due to air, if we don't worry about the fine points about oxygen versus nitrogen, if we just think air, the propensity for bubble formation at a depth greater than 3 meters is 0 or negative. So there wouldn't be. That's the reason Ebel said that his salmon in the confined situation at the bottom of the cage didn't get gas bubble disease. So you ask yourself the question, well, why didn't the dumb fish in the deep cage just stay down in the bottom, they could have avoided gas bubble disease too, but there's obviously no mechanism that was available to those fish to tell them, hey, you know, it's dangerous up near the surface. And I'll explain to you what I think was going on that was the failure of a signal to cause those fish to respond in the way that you and I would logically think would be adaptive. But you and I have got, you know, Weiss saturometers to use, and these fish don't have them, and I'll tell you what a Weiss saturometer is in a little bit. Yeah, Chris has a question about that.
So according to that, all fish that stayed 3 meters or deeper had no...
Yeah, in the cage experiments that Ebel did, the fish that stayed or were forced to stay at a depth greater than 3 meters developed no gas bubble disease. But apparently in the cage that went all the way to the surface, all of the fish moved up and down, and didn't stay below 3 meters. They came up to the surface periodically, and something about that caused them to develop the gas bubble disease. It looks 68% of them died in 7 days. So some more things about gas bubble disease. One is that nitrogen seems to cause symptoms of gas bubble disease anytime the absolute saturation of nitrogen is 110%. And you get serious mortality whenever it goes above 130 for nitrogen. What about oxygen? If you keep nitrogen at 100% absolute saturation and let oxygen go above, there haven't been any cases that I know about where there's been gas bubble disease caused by oxygen, only when only oxygen is supersaturated. I guess being so metabolically active that the oxygen is used about as fast as it comes out of solution and doesn't therefore seem to cause gas bubble disease. So all the cases I know about where there's been gas bubble disease, it's been nitrogen that's supersaturated or total air. And usually if it's one, it's the other. In other words, there's so much, since air is 80% nitrogen, anytime nitrogen's supersaturated, then the total gas tends to be supersaturated. How long does it take? Apparently that's got to do with how long it takes for the gases to diffuse and equilibrate throughout the fish. And the usual numbers are 30 to 90 minutes. So in a half an hour, you can start to get supersaturated blood if you're in supersaturated water. Maybe faster than that, because most of the fish that this has been done with have been, eaten-sized fish. If you're dealing with a little bitty fish, it might be a lot faster, I would think. Because, why? Some experiments that we've done on circulation times would suggest that in fish that are 10, 20 grams, it only takes 30 seconds for the blood to go from the gills to the core and then back to the gills. About 30 seconds or 30 to less than a minute for a full trip. Now, not all the blood is making the pass every time, and so it may take several loops before all of the blood reaches equilibrium in terms of plasma saturation levels of things like nitrogen. But 30 to 90 minutes is the literature. How do you measure the partial pressure of nitrogen given the fact that nitrogen's an inert gas and you just can't, measure the reaction rate or anything like that? I mean, there isn't a DO meter for nitrogen. Well, there is sort of. It's called a Weiss saturometer, and this is a picture of the actual instrument. There may be new versions that are fancier now, I don't know. But what this amounts to is a very long, thin-walled tube wrapped around and around and around, and you can actually see the tubing inside this protective frame. Plugged at one end, and at the other end it's connected to a pressure meter. And what it actually measures is the pressure exerted by the gases that diffuse out of the water through the wall of the tube and create a positive pressure inside the tube. And then you have to subtract the pressure exerted by oxygen, which you can measure, and by water vapor, which you can calculate. And the difference, you assume, is the pressure of nitrogen. So that's the way in the good old days at least, that's the way we determined whether or not water was supersaturated and how much with nitrogen. There may be new techniques that involve new technology that have come along since this? I don't know. Do any of you guys know if there's an instrument that measures the pressure of nitrogen in water directly? I don't know of one. It makes sense. It'd be hard to do because nitrogen is so non-reactive. You can't get it to do anything except create a pressure. And that's what it's doing in here. So you understand the principle there is that over time, the pressure of the gas in solution reaches equilibrium with the pressure of the gas in the void of the tube. And that pressure that's in the void of the tube can be measured as an actual, hydrostatic or gasostatic pressure. It takes a long time to do this. It's not any fun to make measurements because you got to jiggle this thing to keep the water right around the little tubes replaced with new water all the time. And you got to do it long enough to get to equilibrium. And that usually is 30 minutes or so of jiggling before you get a steady state. So those of you who have done this kind of work or water quality work know that with the old membrane type DO meters, you have to jiggle those too, but you only have to jiggle them for a minute or so to get steady state there. But with this thing, it's like half an hour. Okay, that's it for that. We move on and talk about something that is related, very much related as it turns out, and that's swim bladder dynamics. Swim bladders are one place where fish do have sort of the equivalent of a Weiss saturometer as far as the gas pressures are concerned. And so it may turn out that there's some connections here as we move along. The function of swim bladders, the primitive function of swim bladders seems to be to allow the animal to be neutrally buoyant, because the liquids and the solids that make up living organisms tend to have a density greater than water, unless they're pure water. Most animals are only about 80% water, and things like bone weigh more than water. And so if you want to obey Archimedes' principle, which says you're going to float neutrally buoyant in the water only if you displace a volume of water equal to your own weight, then what you have to do is average out the weights of tissues that are heavier than water with something that's lighter than water. And gases are much lighter, so that'd be the logical thing to use. In the case of real deep sea fish, where gases may be a problematic thing, they tend to use oils, which can be lighter than water too. So the primitive function of gas bladders is buoyancy regulation, and only secondarily have they come to be used for gas exchange for respiration and function in a lung-like way, or an accessory respiratory structure. By habitat, the fish that live in freshwater, most of them have swim bladders, with the exception being benthic fish. Fish that have, for a lot of their evolutionary history, lived on the bottom, like cottids, sculpins, some of the darters that are benthic fish have lost their air bladders secondarily. In marine habitats, frequency of swim bladder occurrence goes down with depth. When you're near the surface, most all the fish that live free swimming in the upper layers of the ocean have swim bladders, but as you go down deeper and deeper, the swim bladders become reduced and finally go away, and the gas that might have been in them when they're living near the surface, in the forms that live near the surface, have been replaced with oils at depth. Taxonomically, some fish that don't have swim bladders, one really important group are all the sharks, all the elasmobranchs. They do not have swim bladders. Some of the primitive bony fishes like coelacanths don't have swim bladders. The cyclostomes, the round-mouthed fishes, the hagfish and lampreys don't have swim bladders. In other primitive forms, the swim bladder is not only, it serves as a lung, basically. In fish like gar, experiments have shown that if you take gar and you prevent them from coming to the surface, as they would be apt to be prohibited from if they were trapped in a gill net, let's say, they suffocate because they can't get enough oxygen, especially if oxygen is low in concentration in the water. They can't get enough just from their gills. They have to supplement that with aerial respiration. And there's even folks who have studied the frequency with which gar surface and take a little sip of air at the surface, and it increases with temperature, for example. So the frequency with which they come to the surface and air breathe is increased by increasing temperature because the demand for oxygen is increased by increasing temperature, and maybe the solubility as well. Other fish, by the way, and I don't know if I said this when I talked about respiration, but a lot of fish, particularly surface adapted forms like top minnows, don't really necessarily breathe air, but they do make an effort to make sure they collect the oxygen that's in that surface film that's right beneath the surface, because logically the water just beneath the surface in a stagnant situation would be the water with the most oxygen. And so they go along and they just sip that layer and breathe that instead of going down and getting the deeper water, which would be without as much oxygen. Several of the advanced bony fishes have lost their swim bladders secondarily. Benthic forms, but even some that aren't benthic, like tunas, for example. Some of the tunas essentially have no swim bladder when they're adults. They may have a swim bladder as juveniles. Even the ones that do have swim bladders aren't able to achieve neutral buoyancy with their swim bladders. Their swim bladders are not big enough to offset their mass, so tunas have to swim in order to breathe, as well as swim in order to stay up in the water column. So they swim continuously for two reasons. This ramjet ventilation we talked about, where you open your mouth and you swim and use the force of forward movement through the water to actually irrigate the gills, that's one reason. And then secondarily, they swim just to maintain the depth at which they're located. It's called hydrodynamic equilibrium as opposed to hydrostatic. Essentially, they fly through the water, achieving lift by their movement. I already mentioned there are two different classifications of fishes that do have swim bladders, and it depends on whether or not there's a tubular connection between the gut of the fish and the open lumen of the swim bladder. And that tubular connection is called a pneumatic duct. It forms as an evagination from the dorsal side of the esophagus. And it's present in the more primitive fishes, the soft-rayed fishes. And the main groups that have this pneumatic duct are things like herrings, salmonids, minnows, and catfishes. The other group are the more advanced fishes, more advanced bony fishes, the spiny-rayed bony fishes, things like centrarchids or sunfishes, for example, bass and red drum, red snapper. Those fishes are said to be phycoclists, and that label indicates a fish that has a swim bladder but no tubular connection between that bladder and the gut. Perches, cichlids, sunfishes. And then there's a third group that's sort of a hybrid group, not hybrids in a genetic sense, but in between, intermediate group, and that's the paraphycoclists. And those are the fishes that have tubular connections when they're young, juveniles, but they lose them as they get older. The biggest group and the best representative there would be myctophids, or the lanternfishes that are midwater marine fish. So what's in that swim bladder? Well, it's gas, and ordinarily it's a mixture of gases much like air, especially if you're talking fish that live near the surface and especially if you're talking physostomes. But in deeper water forms, both physostomes and physoclists, the gas mixture in the swim bladder can vary markedly away from an 80-20 mix of nitrogen and oxygen to something that's almost pure nitrogen or something that's almost pure oxygen. And research has shown that in the case of these extremes, what typically is the case is that a fish that's moving down in the water column tends to be richer with oxygen, and a fish that's moving up tends to be richer in nitrogen. And the logic there, or the explanation, is that fish that are moving down are having to put gas into the swim bladder to maintain the volume of the swim bladder against that greater pressure. And so they're secreting oxygen into their swim bladder. Fish that are moving up need to reduce the volume of their swim bladder because it's going to swell up as the pressure goes down, and oxygen tends to diffuse faster than nitrogen, so you're left behind the nitrogen in the swim bladder as the fish moves up. So the compositional changes in these gases reflect the dynamics of the swim bladder. The diffusivity is the proper word of the two gases, as well as the secretory effect of the gas gland and the swim bladder reap that I'll talk about next. I guess I alluded just in passing there that the swim bladder, is being a sac of gas, and a reasonably elastic sac of gases, tends to follow Boyle's law, which says that pressure and volume are inversely related if you don't change the amount of something. Another way of saying that is that the product of pressure and volume of the gas in the swim bladder at one depth or under one set of conditions is a constant, therefore the same as at another set of conditions. So if one changes, the other one's got to change in a compensatory way to maintain the product at a constant value, unless some gas is either taken out of the swim bladder or put in. When fish rise in the water, the pressure goes down because the hydrostatic pressure exerted by the water is reduced by 1/10 of an atmosphere for every meter. And so the volume of the swim bladder has to increase unless some gas is gotten rid of, unless some gas is removed. A little calculation just to quantify things. Let the volume with subscript ESB be the equilibrium swim bladder volume, the volume that gives neutral density to the overall fish. If the fish, however it got there, is neutrally buoyant at a depth of 2 meters, in other words, it's got enough gas in its swim bladder to exactly offset the difference in the mass of the rest of it, so that it's neutrally buoyant. At a depth of 2 meters, it's got volume equal to ESB, or equal to VESB. What happens when it moves up in the water column? We can do the calculation because Boyle's law says the product of pressure and volume must be the same. And we know that at 2 meters, the total pressure is 1 atmosphere of air and another 2/10 of an atmosphere of water pushing in on the volume of the swim bladder. But the volume is resisting that at equilibrium. So we got 1.2 times the equilibrium swim bladder volume at a depth of 2 meters. Now the fish comes up to 1 meter. Well, the pressure went down by 1/10 to 1.1. And so what's the new volume? Well, the new volume is 1.2 divided by 1.1. I'm just going over and dividing that 1.1 into that 1.2 to calculate VSB under the new conditions. And the calculation says we end up with 1.09. So the swim bladder volume increases about 10% when the fish comes up that 1 meter. Comes up another meter all the way to the surface, what happens? Well, then you've got 1.2 over 1 even, so it's 20%. When the fish sinks, the pressure on the swim bladder increases, so the volume's got to go down. Unless we do something to add gas, to deposit gas. So if again, going back to the same set of conditions, starting out at 2 meters with an equilibrium swim bladder volume, what happens if the fish goes down to 3 meters? Well, we just do the math, and the result is 0.92. And so here's the important conclusion here, and it's Archimedes' conclusion. It is that without a change in the amount of gas in the swim bladder, fish can be neutrally buoyant at only one depth. In this case, it was assumed we started off equilibrium at 2 meters, and so it's neutrally buoyant only at 2 meters. It moves up, it gets light on its fins, and tends to float toward the surface. It moves down, the pressure compresses the swim bladder gas, making the fish heavy, and it tends to sink. And you can demonstrate that kind of thing, with a bottle with a little bit of sand in it and air in it. You can hold it in the swimming pool and let it go. You figure out what the proper depth is for neutral buoyancy. Well, you need more than a bottle. You need a bottle with a balloon on it because you need to be able to change the volume, right, with change in pressure. In other words, you have to obey Boyle's law. You have to have an elastic bag of gas, and a bottle is not very elastic, but it would be if you put a balloon on the end of it. So, without a change in the amount of gas in the swim bladder, fish are neutrally buoyant at only one depth. And what's that depth? Well, it's the depth at which the ratio of the weight of the fish divided by the volume of the non-swim bladder tissues plus the volume of the swim bladder. In other words, the weight divided by volume is density. And when that ratio is equal to the density of the water, whatever it is, then you got a neutral buoyancy situation. The density of the water is different if it's seawater, if it's fresh water, and so fish that live in fresh water tend to have slightly larger swim bladders than fish that live in seawater, because fish that live in seawater don't have to displace quite as much gas in order to achieve the neutral density. They tend to float a little bit more. Okay, so for the volume of the swim bladder to be constant, given no deposition or removal of gas, then the pressure inside the swim bladder has to be equal to the pressure outside. If either one of those is different from the other, if one is different from the other, then the swim bladder is going to be expanding or it's going to be contracting if the bladder itself is elastic. It's not quite elastic. A guy named McCutcheon years ago worked out that the body walls of the fish, impose some constraints on this purely elastic Boyle's law type swim bladder. It's not just a balloon. It's a balloon with a surface that's with a surrounding set of tissues that constrain. And I think what McCutcheon found out was that fish can actually be neutrally buoyant in effect with about a 5% over or under volume in their swim bladder. In other words, they got a little bit of room to maneuver. They go more than that, then it tends to still be overinflated or underinflated. Here's another point and it took me a while to figure this out. It probably wouldn't take you long, I hope, especially if I emphasize it. And that is that the pressure that's inside the swim bladder has to be generated by gases in the gas phase. That's all there's in there. I mean, if we're not talking about oils, if we're talking about gas. So the pressure inside has to be generated by the gases. The pressure that's outside, though, is generated by air pressure, the weight of the atmosphere bearing down on the water, and by hydrostatic pressure, the weight of the water above the fish. So in the case of the outside pressure, it's all hydrostatic pressure or atmospheric pressure. The partial pressure of gases in solution have no bearing on that outside pressure. On the other hand, the partial pressures of the gases and the gas that's in the swim bladder are all important. That's the only pressure there is. So, pressure of gases in solution do not contribute to the pressure outside. So at steady state, the pressure of the swim bladder is the partial pressure of oxygen in the swim bladder plus the partial pressure of nitrogen in the swim bladder and any other gases, but we'll just assume that everything is oxygen or nitrogen. And that sum of the two partial pressures has to resist and be equal to the pressure of the atmosphere bearing down on the water plus the pressure of the water itself. So that's 1 atmosphere of air and 1/10 of an atmosphere of water per depth, per meter depth. So that's the rule. I mean, if this is not an equality, then the fish is either gaining or losing. It's moving, it's changing its volume. It's a dynamic situation. It's not a steady state. Deposition of swim bladder gases under normal circumstances, but I'll tell you later on about some abnormal circumstances that turn out to be closely connected with gas bubble disease. Under normal circumstances, there are 2 sets of mechanisms. There's air swallowing. In the case of physostomes, go up, get a bubble of air, basically swallow it down the esophagus and squeeze it by muscular force into the swim bladder through the pneumatic duct. There is the possibility that's been recorded in the literature of fish actually grazing on bubbles of pure oxygen that are being produced by plants, macrophytes that are engaged in heavy photosynthesis in stagnant water, eating those bubbles. But I think there's some debate about whether the bubbles actually get into the gut and into the swim bladder. Some people have suggested that could be a way why you get oxygen-rich swim bladder gases. But the main method, obviously, is to go up to the surface and swallow air. And it's critical in larval physostomes like catfish and salmonids to get that first air bubble, because the fish hatches out, with nothing but solids and liquids in its little body. It's yolk and it's the egg. And so during development, when the swim bladder forms, that first filling of the swim bladder has to be achieved by swimming to the surface and swallowing an air bubble. It's such an obvious thing and such a critical thing, it's got a name. It's called the swim-up stage. And lots of mortality in little catfish and little salmon can occur at swim-up. Fish that don't succeed one way or the other. But adult fish do it too, adult fish that live near the surface. But what about adult fish that live deep in the water column, like lake trout, that may never get within 50 meters of the surface? Obviously that's not a mechanism for them. So some of the physostomes rely on a second mechanism, which is the fundamental and the only mechanism available to physoclists, and that's actual secretion of gases from the blood into the swim bladder. So what happens is the fish is breathing the water through its gills. It's getting oxygen. It's getting nitrogen too. And some of that gas then can be actually secreted into the swim bladder, going from dissolved form to gas form as it passes into the swim bladder. Physostomes do a little of this, but it's the only method that physoclists have to work with. Okay, here's how it works. Yeah, Chris, I have a question.
I was just going to say, how quickly is that process? Is it fairly quick, or does it take
It takes a while, and I think I've actually got some numbers a little later on in the notes. I think I've got some time constants for that process. I'd say it's got a rate constant of about 30 minutes. It's about the same as the rate for gas transfer. 30 minutes to 90 minutes, something like that. It's been measured. We'll talk about that. Okay, here's a generic representative swim bladder. Swim bladders come in all shapes and sizes and in multi-compartments and all kinds of things. This is one that's one main compartment. But then this secondary little compartment off it we call the oval. And it turns out that's an important location because that's where the excretion, I guess you'd call it, of gases occurs. The movement of gas from the swim bladder, from the gas state, back into the blood, which is how the gas has to go. The gas has to go both directions in the blood, right? There's no other way for the gas to get in or out of the swim bladder of a physoclist except through the blood. Let's talk about the gas getting in first. This combination, again, a highly schematized version of this thing, of a REIT, the full name of which is Richa Mirabile, or Miraculous Network, and gas gland achieve the deposition of gas, and the most important one is oxygen. That's the one that's special here. Swim bladder REITs have lots of little bitty vessels. They are the most refined REIT countercurrent exchange system known. Somebody estimated that eels have over 1,000 square centimeters of surface area in the little vessels. In fact, I think the numbers are like 1,200 to 1,700 square centimeters of area for every cubic centimeter of volume. That's some surface area. So they are very thin-walled. They allow oxygen to pass as well as other materials. So there's 100,000 of these little radial elements. How long are they? Well, that depends on the fish, but probably about a centimeter in a, pan-sized fish, maybe. They consist of vessels that are on the arterial side as well as on the venous side. And what we're going to do is just try to go around the circle. We're in another one of these situations where there's no real beginning, so it's hard to start. You have to assume something that's already happened before you can start. So you make a couple of loops, and finally you hope to get steady state in your mind when you do that. And so what we're going to start with is this branch of the celiaco-mesenteric artery, which is just supplying arterial blood to this swim bladder REIT. And we're going to assume that that arterial blood has a pH of 7, that it's got 100% hemoglobin saturated. It's the hemoglobin that's in it's 100% saturated with oxygen. And the partial pressure of oxygen in the plasma is in equilibrium with what's in this surface water, which is 0.2 of an atmosphere. So there comes the blood into this REIT. And I've got two numbers up here. I've got one that's in front here in the middle, it's 100, and then there's 100 in parentheses. And what that's intended to show, the parenthetical values are percent hemoglobin saturation that would obtain if you stopped the blood right there under those conditions and let it come to steady state with the plasma. But this is a dynamic state. This blood's moving, and the conditions are changing continuously, and things take a little time to get to steady state. So initially, though, we are at steady state. We'll assume 100 and 100. Blood moves along on the arterial side of the REIT. And funny things happen. We notice that the pH is going down 7 to 6 to 5. And the partial pressure of oxygen in the plasma is going way up, 40 atmospheres by the time we're midway through here, to 105 atmospheres by the time we're at the other end of that arterial retial element. Oh, I forgot to tell you something important. And that is that what we're trying to do is look at the situation for a fish that's living at a depth of 1,000 meters, where it would have to have, 101 atmospheres of total pressure in its swim bladder to resist being crushed, to resist the swim bladder being squeezed into nothing, right? Or squeezed to a smaller volume than is neutrally. What we want is to ask the question, what would it take to be at steady state, to be neutrally buoyant at 1,000 meters? And you'd have to have a volume of your swim bladder at the equilibrium volume, and it would have to be stable at that level. And how much pressure would it have to have in it? Well, by that rule I just read you, it'd be the sum of the partial pressures of the gases, and that sum has to be 100 atmospheres or so, maybe 101 atmospheres, I guess. Is that making sense? Because we're at 1,000 meters. There's 100 atmospheres of water and 1 atmosphere of air pushing down, squeezing. And that has to be resisted by just the total pressure of swim bladder gases. And most of it, I'm going to tell you, is going to be oxygen. Very little of it nitrogen. Why? Because oxygen is transported to the hemoglobin and can do some what almost seem like magic tricks in terms of multiplication. And I'm going to try to explain that to you. So we're going around this loop. We're on the arterial side. We're up to 40. We're up to 105. We enter this specialized tissue that we call a gas gland that's right there at one end of the reet and right up against the swim bladder itself, the epithelium. And it's in that gas gland that oxygen moves from the blood into the swim bladder lumen. That gas gland is a gland, and it produces something like glands tend to, and what it produces is an acid. And the acid it produces is lactic acid, milk acid. Doesn't produce hydrochloric, doesn't produce malic acid. I'm giving you old alternative exam answers that you're not supposed to select. I'm giving you a hint. The acid it produces is lactic acid. And what happens is, as that blood flows through the reet, we have got, by magic trick almost, it looks like, 106 atmospheres of partial pressure of oxygen in the plasma. And that's a greater partial pressure than the pressure we need over here in the swim bladder. So we got 106 to 100, so that's going to drive oxygen into the swim bladder, right? All right, however we got there, and we're going to get to how we got there as we come around the other side. Now we're in the venous side, return side of. We've made this hairpin turn in the gas gland, and now we're going to go back out, and we're going to end up in the renal portal vein down here eventually. But before we do, some important stuff happens. What's happened here is that the lactic acid that's being produced by the gas gland is dissociating hydrogen ions, and those are causing the pH to fall in the blood plasma because it's not very well buffered. If it were well buffered, we'd be out of luck, Valdemar. So it's a good thing it isn't well buffered because we need the pH to go down. And the pH goes down to 3.5 at this extreme. That causes a root-off effect. In other words, the hemoglobin can't hold much oxygen when the pH is that low. In fact, it can only hold 10% of the saturation amount, we claim. And it's a steady state because the root-off is fast. Dropping that handful of jacks or marbles or whatever it is quick, so it's easy to get rid of. Take that oxygen off that hemoglobin and into the plasma. So we're at 1010 here. We've got 106.5 millimeters mercury partial pressure of oxygen here because the capacity of the plasma to hold that oxygen that's being dumped off of that hemoglobin is small. It causes supersaturation of that plasma big time. That amount is greater than the amount on the other side. That's only 105. And so we got a partial pressure gradient favoring the diffusion of oxygen across the reet from the radial elements that are venous into the ones that are arterial. And that's what's causing this pH to drop on the other side. Well, that's not what's causing the pH to drop. That's what's causing the PO2 to rise, is because the oxygen's diffusing across. What's also diffusing across is the hydrogen ions from the lactic acid dissociation. Lactate's a big old fat molecule. It's not going to move, so it goes on out, and it's the cost. You have to produce the lactic acid, and you're going to have to throw away the lactate eventually. So the lactate stays in the venous blood, but the hydrogen ions tend to seek their equal concentrations, and so they diffuse across to where they're less concentrated. That'll be where the pH is higher. And so as we go along the reet here, and all this is happening in a second, because that's how long it takes for the blood to pass through this 1 centimeter tube. As we go along the reet, the pH fall arises because we're losing the hydrogen ions to the other side. Simultaneously, we are losing oxygen to the other side because it's diffusing across in the direction of its partial pressure gradient. And the percent saturation at steady state is going up because the pH is going up. And notice that when the pH is 5 over here, the steady state percent saturation is 60, and that's the same as over here on this side. So we haven't told any lies here or misled. I mean, we've got the same dissociation curve on both sides of the REIT. The only thing that's different is on this side, the percent saturation is increasing. We're having to do a root on. Remember, root on is slow. So what's happening is the oxygen is taking a while to get back on the hemoglobin. And at this point, we've only got 15% actually on the hemoglobin of saturation, but we've got a theoretical capacity of 60. Why don't we have 60? Well, because it takes a while. And the blood's moving, and the conditions are changing. And by the time that reloading of oxygen onto the hemoglobin can occur, the blood has already left the exchange arena and left in the renal portal vein, so it's no longer susceptible. So we end up with blood coming out of here at 3/10 of an atmosphere of oxygen, which is more than 2/10, which moves it across still a little bit. We end up with 6.5 pH, which is more hydrogen ions than 7, so we're still getting hydrogen ions going across at this point. The theoretical steady state percent saturation of the hemoglobin has gone up to 90, still lower than 100, but it's at 90. But we're only up to 20 in actual. So, the blood's going to leave the REIT way undersaturated on the hemoglobin in terms of steady state. And that's the trick. That's the trick. It is that we have moved the oxygen into the plasma at higher than you could do without this kind of mechanism involving lactic acid, hydrogen ion dissociation, and transfer across. Have we beaten? Do the laws of mass balance still hold? In other words, how can you start out with only 2/10 of an atmosphere of oxygen in this arterial blood coming in, gain to 100 atmospheres in the REIT, in the swim bladder, and leave here at 0.3? It sounds like you got something for nothing, right? But did you? No, you didn't, because we're leaving with blood that's only 20% loaded on the hemoglobin. So the actual amount of oxygen per unit volume of blood leaving the REIT is way less than the amount going in on the arterial side. So we haven't beaten the law of mass balance here. Two different mechanisms are involved in this, and you can think about this. I threatened to give Ecofish a REIT system and let it have a swim bladder and do things, but I haven't done that yet. Somebody else needs to do that. Two different things are going on that are involved in the secretion of gases into the swim bladder. And the time is up, and I'm not going to keep you guys to tell you what those things are. So I'll wait unless you all unanimously agree that you got to hear the end of the story. I haven't heard anybody saying, yeah, go. So we'll just stop right here and pick it up. We've only got a couple more slides to go on this, and then we'll talk bioenergetics. That's the thing of most interest to aquaculture, probably. We'll do that next time. Thanks for your attention.